I'm from Bitfury. I studied at the KPI, and I received education at computer systems and networks. Managed to work on variety of so ranging from embedded systems and NA with supercomputers. Just over a year ago, I joined Bitfury to help develop the blockchain framework Exonum. Bitfury is a global blockchain technology company, one of the few that has products in the field of hard and software. So, the most famous of the hardcore products, there are some of the most efficient Bitcoin mining chips in the world. Of our software products, the most well-known is Exonum, a framework for building blockchain applications. A Crystal, so it's a it's an application for blockchain transaction analysis for conducting various investigations, and Peach. This one is a third level protocol for Lightning networks which speeds up payments of Bitcoin network and makes them more accessible. I'm here today to tell you about the first one, about the Exonum. We'll start with a brief overview of the capabilities of this framework, then consider how you can expand it to implement smart contracts, configure and launch a network of Exonum nodes that will execute this smart contract, and if time permits, we will consider the implementation on light clients for applications on Exonum. First thing first, I would like to ask the audience who among you is familiar with the differences between open blockchains and closed ones. Please raise your hand. Well, perhaps a little bit to tell about this topic. I'm sure many of you are familiar with open blockchains. The most famous examples are Ethereum and Bitcoin. In such networks, any person can become a member. Anyone can join and not only get access to all transactions in the system and restore the current state of the database, but also anyone can send transactions to the network and receive new blocks. In such a system, you need some mechanisms to prevent bad behavior. In order to prevent damage to the state of the database, that you have some conflicted forks, and you also need mechanisms to encourage good behavior. In the case of Ethereum and Bitcoin, this is a cryptocurrency. These mechanisms are implemented in the algorithm, in the consensus algorithm that in such systems based on fairly time-consuming algorithms such as proof of work. Such open systems, due to the fact that anyone can see transactions in the system, are highly secure, but the speed of such algorithm, unfortunately, is rather low. There is, in this case of Bitcoin, tens of transactions per second, but the blockchains are closed. Only a limited number of participants can join them. They are known, the relationship is governed by some agreements in the real world. So, special intensification isn't necessary because they themselves are interested in the fact that the system worked correctly. In such systems, faster consensus algorithms are applicable, but if clients who are not authorized to see all transactions need to access the system, request some data, solve some data, then the level of trust is not high. Because you cannot see transactions, you cannot see all the data, you cannot be sure that they are actually stored there. This problem can be solved by the Exonum framework for building private blockchains. It does not contain any business logic. It's the basis for building your blockchain applications. It provides an opportunity to write smart contracts with arbitrarily complex calculations. While preserving complex data structures in the repository, and with it, you can implement arbitrarily complex smart contracts. Exonom does not include a really made network of nodes. You configure it and run it. Typically, there is a decentralized network. There are several participants who agree to perform some smart contract on this network. Exonom uses a consensus algorithm that is resistant to Byzantine behavior. Byzantine behavior is when a node actively tries to disrupt the system, sends unknown transactions, votes only for its transactions, tries to filter transactions. Due to the fact that the number of nodes is known and limited, it's possible to achieve high throughput. Exonom has a throughput of 5,000 transactions per second and a transaction acceptance rate of less than a second. ED 25519 is used as a digital signature algorithm. Another Exonom feature is anchoring. Anchoring can be compared to monetization in the real world. When you come to notary, and he does in his journal, his registry makes a record of some document that is correct. In Exonom, there is anchoring service which allows you to do a similar thing, but with the state of the database. You publish at some point in time the state of your database in Bitcoin, which is known to be significantly more resistant to change than any closed system. In order to break a Bitcoin, you need to spend an astronomical amount of money, and anchoring is such a way to preserve the state of the database of systems so that, even in the event of collusion of all nodes of a private system, it would not be possible to rewrite this state so that customers will not notice. Opportunities for verifying evidence for verifying anchoring are included to the JavaScript library, which allows you to integrate your application, your browser application, with the Exonom framework. Similar library is also for Java and Rust, and the main features are sending a transaction to the network, data verification, verification of evidence that some data is in the database, as well as anchoring. A little about the evidences. I'll tell you a little more about how they work. This is a such system, a complex structure that allows you to prove that a certain value is in a database, in a certain collection with a certain key. Moreover, such evidence does not reveal other keys in the system. Evidence is needed for light clients so that they can verify their data without having access to the complete node that performs all transactions. Those, at the expense of anchoring and at the expense of evidence, using the framework, you can achieve the level of security that is characteristic of open blockchains, but at the same time, control all the other aspects that allows private system. Now let's look at how you can extend this framework using Java, how you can implement smart contracts. Well, to implement smart contracts for Java binding is implemented from the user's point of view. There is also a framework in order to define smart contracts and then execute them in terms of the implementation of this contract for a growth framework. Yes, by the way, the core of the framework itself is implemented on Rust. Please raise your hand whoever wrote in this language. This well illustrates the popularity of the language and why we decided to write Java Bunny, because not many developers came across it. It's an excellent language for reading complex systems, right, where it's necessary to ensure security during execution. But for the implementation of business logic, they are also suitable, but due to the fact that the community is small, another more popular language was needed. We published Java Bunny literally a month and a half ago. He is in state of alpha. Open under the Apache 2.0 license. And we decided to publish alpha in order to get your feedback as early as possible in order to take it into account in the development of your features in development. We will now consider how to build a blockchain application using Exonum using the example of a simple cryptocurrency. In the cryptocurrency, there will be users who can create wallets and transfer money from one wallet to another. Then we will launch the application on the network of nodes that will work on my computer. In Exonum, there is a service abstraction to represent a smart contract. The service allows you to determine the stored data, the schemes of this data to process the event that occurred in the system. For example, a new unit is accepted, a transaction is accepted. The service also determines the transaction processing rules themselves, what they do with the stored data, and also defines some interface that allows you to access this data from an external system. The interface looks like this. Perhaps we will not stay on all methods. It's identified by some numeric identifier that allows you to track transactions that belong to this service. It also has a name that is used to identify its open interface. Other methods are related to the features that we will look at later, so we'll skip them for now. And for our cryptocurrency, we define just such a simple implementation. Since the blockchain is a special kind with a decentralized database, storage is an integral part of the framework. To save the data of your smart contract in Exonum, there is a collection. A collection is names for data structures that are very similar to corresponding in-memory structures, such as lists, sets, and tables. A special type of collection is a collection of Merkle. Proof list and proof map that make it easy to provide clients and the very cryptographic proof of key contract. The kernel itself uses the same collection, for example, to save all transactions that have ever been processed by the system. Who knows what hash tree is and how is it calculated? Super, I'll tell you a little more then. Here's a complete binary hash tree. In such a tree, with leaf nodes, they are located right here. These nodes store some values that are placed in this collection is gate. The key is derived from the path from the root Merkle root hash node to this element. This way it defines the key. A label is associated with leaf elements. This label is a hash of this element, with intermediate nodes in this picture. The H0 and H1 label is a hash of the children. Thus, the root hash, its value is influenced by all the elements and all the keys that are placed in this collection. This structure allows you to effectively verify the state of large amounts of data due to the fact that when changing a value you need to update only the hashes of those subtrees that contain this element. The remaining subtrees do not change. Also, if you add an item, you update only the tree that, like the trees that contain it. Such data structures allow you to verify the state of the system, the state of the database on different nodes. because all collections that store user data and kernel data are added to one aggregate collection. The illustration shows the user below. They store some of your data, such as wallets or transactions, but the unique identifiers of these collections, the root hashes, are added to the aggregate, resulting in a single database state hash, which is written to each block. This database state hash displays all the elements contained in the blockchain. Accordingly, you cannot change any of them without affecting the state hash. The state hash is also written to the block, thus affecting the hash of the block. Namely, with the help of anchoring, you publish a hash of the block from time to time to the Bitcoin network. Having done this, you can no longer, even with the collusion of all nodes, change any blocks, exclude transactions, replace any user's wallet without changing the state hash, or changing the hash of the block. I gave an example interface here. As you can see, it's very similar to the interface of a regular map, and with a couple of additional get proof methods for obtaining the same proof and get root hash for accessing the root hash of this collection. These collections are used with the service by defining a schema. A schema is a simple set of named collections. Well, when creating these collections, you specify the type of stored items. The elements themselves are stored as an array of bytes. The framework does not interpret them in any way. Access is not carried out directly, but through specific objects that control it and prevent changes in those moments when it's not worth doing. So, you can change any collection only during the execution of a transaction and never more, so that all changes are tracked during the transaction processing and the consensus algorithm process. If you define a scheme for our cryptocurrency, then you should first think about what data we want to store. We have a very simple scheme. We just store wallets by the owner's public keys. Here it is, a method that creates the collection by its name. CryptoDate wallets passes its name, passes the database access object that we pass to the designer, and serializers for public key and for wallets. There is also a method like getState hashes. It's necessary to inform the framework about the Merkle collections that are used by this service. And this method is needed just to aggregate them all into one root hash. Let's see how this evidence itself works. Evidence is available for the Merkle collection and it does not reveal anything of this complex structure except the requested key and value. They are used to prove to light clients the contents of some data in the system. If you look at the structure of hash tree, it will look like this. We have already seen here the proof of the Merkle for such a structure will be the hashes of those subtrees that do not contain the desired element. In this case, this is a hash of this subtree which does not contain, and a hash of this subtree which does not contain the element, as well as the element itself. A light client, having obtained such evidence, in this case from three components, restores the root hash. This happens as follows. First, it calculates the hash of the element and receives the hash of this subtree, which consists of the one element from one node, merges it with its neighbor, calculates the hash of this top tree, repeats this procedure, and eventually gets root hash. Root hash of this collection. If I give you this structure for a wallet, will it be enough to make sure that your wallet is actually in the blockchain? Who thinks this will be enough? Good, thank you. Not really, because all the evidence proves that I have some structure that contains this element. Contains according to the key you requested and leads to such a root hash. Whether this collection is contained in the blockchain, whether it's contained precisely by the name that I'm interested in, this evidence doesn't confirm. For this, there is a so-called complete proof, which includes all of this. Below the evidence that we saw on the previous slide from a custom collection with wallets. Also here is a proof, just above, from the aggregated collections which confirms that the collection that the unique identifier of the given has exactly such root hash and together with other collections leads to such a hash of the database state. In addition, also we include in addition to these two components, we include the block itself, which should contain just such a state hash, which we calculated at the previous stage, as well as number of messages signed by precommits. Precommits messages are such a specific kind of messages, of consensus messages, that nodes exchange during their work. This includes the hash of the block that the nodes are going to accept. Since they are signed, then the validator public key is unknown to you. Then the validators cannot refuse the fact that they agreed to accept this particular block. The block with exactly such a database, state hash, and that at the time the value that the Bob requested was contained in the wallets collection. Here it is. 4 such components that allow you to confirm the fact that the database actually contains what you requested. This is equal to create a complete proof. It includes all of these components. It's not yet in alpha, but it's in the Rust version of the framework. Go to the transaction. Transactions define the processing rules, the rules for processing the parameters of the transaction processing rules. They are executed by atomic operations, they are authenticated using a digital signature algorithm, and are executed in a certain order which nodes in the process of consensus receive. Transactions are inherently associated with a message that forms a lightweight client and sends exonym nodes to the network. The message contains a header that allows you to identify this message from, among others, some parameters of the transaction in the message body, as well as a digital signature. The interface looks like this. There's a method for checking this transaction, a method for executing it, for applying its results. We need to define 2 transactions, one to create a wallet and another to transfer funds. To create one, we transmit the message that we received from the client, check it using the digital signature algorithm, and use the scheme in execution, which we determine to make some changes to the database. Here we just check some preconditions that such a wallet is not in the system, and then end it. The money transfer transaction looks similar. So there is also a message constructor here, the same verification method. Execute is a bit more complicated because here we check all these conditions that must be met before transferring funds from one wallet to another. So we check that we do not transfer to ourselves. Yes, we check it here. Here we check what the wallets of such users really contain and finally update the balance. We also define a transaction conversion method. Each service should define some kind of interface for interaction, and for this, the framework has a framework for defining a web interface. As a rule, you define with it some methods for receiving data, as well as methods for sending transactions. Perhaps we will not have time to consider the issue of determining API services, so it's better to look at the demo of the system. I will launch a couple of nodes, configure a couple of nodes. I have a script prepared because it's long enough. Not so long. This is a process that involves several steps because a blockchain is a decentralized system, not just a distributed system that exists on many nodes. It's decentralized with many administrators, and they need to coordinate their work in order to securely configure the system. This includes 3 steps: generate global configuration for all nodes, then the generation of public and private parameters, and finally, the unification in one configuration. Then I do it all on one computer. So, but something went wrong. Okay, so today without a demo. Native application and, well, yes, I rebuilt. Unfortunately, building a native application will not be so fast, therefore, we can have a little more about API services. Excuse me, how much time do I have? Hope is gone. Well, they consider the services and finish it. API allows you to accept transactions from light clients. The typical processing method look like this. In general, it's plain to transfer it to the framework itself because it almost always looks that way. You accept the message from the packet parameters, convert it to an executable transaction, one that's understandable for the service, and which it can apply to the state. Then send it to other nodes using the service, and the service checks that it's correct from the wallet, and we just answer the hash of the transaction, the hash of this message. This hash is used as an identifier of this transaction for any subsequent requests. Here is an example of a reading method. Here we request a wallet that is identified by the owner's public key, and we request this wallet from the service. If it exists in the database, and return information about this wallet. If not, then return that it was not found. The corresponding methods in the service for sending transactions look like this. This method will just check it out. For reading like this, using the object of access to the node and the scheme defined by us, we request information about the wallet from the wallet's collection and return it to the client. Yes, so we also need to define API handlers. To do this, use the create public API handlers method. To tie everything together, juice is used to manage dependencies. The service implementations themselves are defined in the model, and the service converters in a separate model. Good. Then perhaps this will complete. Thanks for attention. Additional information about the framework can be found on our website. All that I have been talking about is published on GitHub, is available for use without any restrictions. Therefore, you can experiment by defining smart contracts for both Gross and Java, and integrating this application using the light clients that are available there. Thanks. Now I will show a demo. You can already ask questions. Perhaps questions, because you can still run the compilation. If someone has a question for demo, let's ask. There's a list of questions. First of all, who do you consider your competitors and your main advantages over them? Competitors are the frameworks that allow you to implement blockchain applications like Hyperledger and NEM. Yes, I heard about your frameworks, so I have not tried. Speaking about the main advantages, it's a built-in mechanism for notarization, anchoring, which allows you to publish the state of the database in Bitcoin and thus prevent its modification. Subsequent modification without the fact that customers will see it. Also, our system, compared with Hyperledger, by default uses a consensus algorithm that is resistant by Byzantine behavior. By the way, anchoring is also resistant to Byzantine behavior. Here it is. You don't need to perform any additional actions. Also, Exonum, since it's implemented on Rest, is implemented in order to ensure high speed of operation. It provides a sufficiently high throughput. Okay, that's it? Can someone else be from Exonum? If you can answer, you can just pass the microphone. I have another question. Okay, let's consider the question closed. Price issue. This is your commercial product, right? Yes, this is our commercial product. But at the moment, everything I've talked about, the kernel itself, Java binding, light clients, anchoring, everything is available for free. Available under the Apache 2.0 license, which allows you to use this for any purpose without even connecting with us. Okay, well, for example, there is some company, corporation that is interested in your decision. How does it come to you? You train them, or just there's a code there, take it, sort it out? No, of course. We are open to cooperation, and for a little more than a year since Exonum was published, we have implemented many projects as ourselves. Can you provide some examples right away? Project in Georgia. A project in Georgia is a land registry. Now, any operations involving the transfer of land from one citizen to another, they are published. They are carried out on the blockchain and they are anchoring daily to the Bitcoin network. Project in Ukraine. Perhaps you heard about it. This is an auction on the blockchain. Auction for the sale of sales property on the blockchain. Project in Kazakhstan. As far as I know, there is one of the registries from the state registries transferred to the blockchain, which is associated with government procurement. There's also a government decision that registries and an enterprise business logic. How applicable is your framework in real business? It allows you to implement arbitrarily complex smart contracts. Well, nothing stops you from applying in other areas, and we did it successfully. For example, we have a Coca-Cola project where we implemented a registry that recorded data about employees, not of Coca-Cola itself, but one of their contractors. So that contractors in fair local management would not be able to cheat and change working conditions after people were hired. So, not only in the public sphere you can apply it, but to solve any problems where you need such a decentralized secure database. Okay, thank you. More questions? Regarding anchoring. It turns out when you anchor data, you only take the hash place in Bitcoin, yes, that's all. Any possibilities for additional information? Placing additional data into anchoring transactions. I'm not aware of this possibility. But if you have such a need, then perhaps you can extend the anchoring client. In order to expand, well, since it's also open source, the anchoring client exactly the same service as any other, you can expand it in order to publish any additional data with the current block hash. But I don't know about such a built-in feature. Well, there are just other blockchains where you can place some data, at least short text on there is number of transactions, some sums, something else in general. It was just me that it would be cool except just hash something else to read there, some metadata which, let's say, is tied inside the project. Perhaps, but you can request any data using either the interface of the kernel itself, for example, information about the transaction, also with evidence, or from the service itself, if you have some kind of interest in the service to get this data. And you can provide them with evidence and build a chain to the last anchor block. If you need to confirm this. If you want to save this directly in this anchor transaction, then there is no such possibility. I understand. Thank you. I have a question. What is a good anchor branch different from the smallest anchor branch? How is it different? Well, perhaps an anchor branch, which will be some kind of a bad node, you simply will not have such an opportunity because multi-security used there. Economically, this transaction is signed by all validated nodes, well, 2 or 3 plus 1 validated nodes, and then is published. If any node publishes inside, then clients will be able to track this. And if in the case of a private blockchain we have a very simple, for example, a collusion mechanism in essence, it's possible to rewrite the anchored blockchain. If it's 2 or 3 and plus 1, they will simply enchant their branch and write history. You will not be able to rewrite because if at the moment when the network was working correctly, you anchored this condition, after that the entire network conspired and anchored completely some kind of incomprehensible data, then the last point you can trust at the transaction, the system worked correctly. Well, if everyone conspired and began to anchor one of the wrong things, then in that case, there was nothing to be done. They can take a block in the past switch and start an alternative history from it and anchor it. Nothing will stop them. In principle, anchoring does not save a private blockchain from centralized collusion. It does not save from that. If they suddenly if all nodes want to change data in the future, but if you have a properly working network, you save some data there and anchor them, then this part you will not be able to change. There is no collusion. Even if there is a conspiracy, then you cannot cancel, because it's a chain of blocks. It's already on Bitcoin. If you change the chain, then the same hashes of all blocks and database state hashes will change. The effect of the change is... Yes, you will know this. Do not quite understand. Can I have it later? Yes, of course. There is one more question. We don't have much time. Just about the blockchain chain. Here we have common hash stored there as database slice, right? Well, that's fine. The hash of the block itself is stored. The finest turns out of all the blocks is like a tree, a tip, right? Yes, let me switch to... My question is following. Let's imagine someone decided to change data and as a result we have the wrong hash in blockchain. People come in and they check and stumble upon an error. It is not coincident, right? We have the fact of an error. And how will we fix it, this error? After all, we don't know where this changes, and we can search for a day or two, sort of which block was accidentally changed especially. And the time that the network hangs is all. What happens if your entire network changes a block? Well, if a block is written correctly and the wrong hash hangs in the blockchain, people come, check, it's wrong. And how to fix? And how to find where the change was made? Wrong this is. We know the fact of the error, but how we will correct it? Where is it located? Yes, that's where it is. We have a common card, not specific, nothing. Just common, it don't match. Some kind of completely insignificant in one of the nodes. Then, according to the general system, we have a failure. How do we find the point of failure? If one of the nodes formed the wrong block, then this block... No, not one of the nodes, the whole network decided to come to terms. They decide the user, they recorded the blockchain correctly, people check, do not match, and now how to fix the network? Everything. Is this one way? Is the network closing? But if you have an incorrect blockchain, if you accepted such a block that violates the integrity of the system, then it's difficult to suggest what can be done with it. Well, what can be proposed is probably all transactions that have been accepted since the last correct block, then re-execute them, but if your system is no longer correct and is wrong with collusion, then the performing transactions is probably not what will be in the interest of the administrator. How to find out at what point? Well... If, for example, users missed this block and noticed an error on the second block, you refuse back and the hash again does not match. The block will often go, and people can check less often. Blocks are often, and people check the state of the database at a certain point in time, if we are talking about requesting some data. And in response, they receive data as of this block. If the proof is incorrect, then the evidence itself does not contain data at the moment at which the system's work has been disrupted. I'm sorry? How will we roll back then? We are rolling back one block, then that is again correct. We will roll back at random as if it does not match a word. So you don't have the opportunity. A correctly working network simply does not have the opportunity to form the wrong blockchain, since the consensus algorithm will not allow it. In the process of work, all nodes agree on the adoption of the block, and they accept only the correct blocks. I understand that. The question is if they conspired. Good. So if they agreed, then the client, he does not have access of the blockchain. It's easy. So it's like client, and all that he receives through the open interface of this service, and from this interface he received data that his data is incorrect, that this evidence is incorrect. Then all he receives is a signal that the system operation has been disrupted. In general, nothing. In general, there is a block, it has 10,000 transactions, one of them changed. Blockchain can only say that there is something wrong. There may be all transactions wrong, maybe one is wrong, well, something is wrong there. How would you just do the audit of the transaction in this block plus? Then it's advisable to make some mirrors. There's still some decisions to make, including decentralized data storage, for example, as additional security. If you have a blockchain, then it implies decentralization. There are many validator nodes. Moreover, it's possible to start nodes of auditors who have access to all transactions in the system, but do not have block acceptance rights. Such nodes can be placed in some trust organization that will not participate in this conspiracy. But again, we're talking about a block. A block is a black box. The blockchain does not know what is in the black box. It encrypted at all. A block, but it's difficult to call it block box because for the nodes auditors, they carry out all transactions. I mean a block of transactions that you need in a conventional centralized system that gave the hash of this blockchain. In the usual centralized, but by centralized you have a client, no matter what. The client probably should know about all nodes because he must know the public keys to check the status of the database. And by default, of course, he will not appeal to all for proof because he only needs one, due to the fact that we include signed pre-commits messages. There is no need to communicate with everyone, but if necessary, he can turn to others. If your system allows it, if it's not limited to any other software and hardware limitations. Thank you very much. Unfortunately, we no longer have time for questions and answers. Tell me please, will you show something or is it all? Unfortunately not. Okay. In general, thank you very much, Dmitry, for your speech. Let's applause for answering questions.
Baby.